Isomerism in alkenes. We have already seen that there are two main groups of isomers, structural isomers and stereoisomers. Structural isomers were characterized by the fact that the molecular formula is the same but the structural formula is different. In the case of stereoisomers, we have the same molecular formula and the same structural formula, but different spatial arrangements of groups around the carbon atoms. As an example of stereoisomers, we are doing cis-trans isomerism. Illustration 26 explains how cis and trans isomers are formed. Because there are not free rotation around a carbon-carbon double bond as in the case of a carbon-carbon single bond, the arrangement of the groups in space is fixed. So if the two big groups in this case, the ones with the circles, are on one side of a double bond, it is not easy to rearrange them so that the big group will be on the other side of the double bond. A lot of energy is involved in this process, so we get two different types of compounds, a cis isomer and a trans isomer, and they cannot be easily converted to one another. Right, so the criteria for a cis or a trans isomer to exist is that there must be two groups that are the same, or two atoms that are the same. In this case, the hydrogen atoms are the same, and they must be situated on one side of an imaginary line through the carbon-carbon double bonds, or they must be opposite. Right. In the case where the two groups that are the same is situated on the same side, we have a cis isomer. In the case where they are situated across, it is a trans isomer. The two groups that are the same may not be situated on the same or bonded to the same carbon atom. Then we don't have any cis-trans isomerism. Let's go and look at examples of cis and trans isomerism, as well as other types of isomerism in alkenes. The typical question asks, is it possible for a compound like this to have a cis and a trans isomer? To look at that question, or to answer that question, we must look if the same group is perhaps bonded to the same double bond carbon. Because there are two methyl groups attached to this carbon atom, it is not possible here to have cis-trans isomerism. What we do have is a compound. In this case, we have got also two groups attached to the same double bond carbon. But these two compounds are actually structural isomers. They are not cis-trans isomers, they are structural isomers. They have the same molecular formula but different structures. This compound here, two hydrogen atoms attached to the same carbon that is part of a double bond system. That means we can't have cis-trans isomerism. This example, if we look at the double bond system here, we have got an H and an H. So two groups that are the same, and they are not attached this time to the same carbon atom. So this makes it possible to have a cis and a trans isomer of this compound. So if we draw one of them, let's draw the trans isomer in this case. That means that the two groups that are the same are on two different carbon atoms, the two H's. They are across the imaginary line through the double bond, and we just add the other two groups. It's a methyl group attached to the double bond system and an ethyl group that is attached to the double bond system. So this is the trans isomer. In the case of cyclic structures with double bonds, a cyclic alkene, we must remember that there are hydrogen atoms attached to these two double bond carbons, and they are situated on the same side of this imaginary line. So this is an example of a cis compound. In a ring structure, the groups will always be cis because they are forced to be cis. They cannot be trans because the ring system is on the other side.